Hey, what's up everyone? Welcome to a new module where we discuss about a new algorithm, classification and regression trees, or more commonly known as CART or decision trees. This algorithm can be used for both regression and classification. So let's do a quick recap. We were talking about supervised learning in the modules that led to this, and we have seen regression, which is one type of supervised learning where the dependent variable is numerical in nature, and we have seen classification where the dependent variable is categorical. And we have seen one algorithm in each of these techniques. We have seen linear regression, which can be used for a regression problem, and we have seen logistic regression, which is used for a classification problem. Now let us look at a new algorithm. So in this module we will talk about CART or classification and regression trees. This is also known as decision trees. This can be used for both classification and regression. So remember, decision trees can be used for both classification and regression. Let us first start the module by discussing how decision trees work in case of a classification problem, and later we will extend the concept to a regression problem also. So please note, first we will be talking only about a classification problem, how a decision tree algorithm works in case of a classification problem where we have label data, where the dependent variable has labels or are categories, and later we will move to a regression problem using decision trees. So let's start with an example first. So let's take an example where I have two independent variables x1 and x2. So these two are my independent variables x1 and x2, and I have my dependent variable y, which is two categories, plus and minus. So instead of ones and zeros, I'm taking plus and minus because they are easy to represent here in a graph. If I write ones and zeros, it might not be very clear, so I'm writing it as pluses and minus. Now what is the goal what is the goal of any classification algorithm? Any classification algorithm tries to separate the two classes, tries to come up with a mathematical function, as we have discussed in the previous modules. Any algorithm tries to come up with a mathematical function which can separate the two classes. So for different values of the independent variable or different values of x's, the algorithm tries to give out the values of y. So give out different values of y as per the actual data. So if f is the algorithm, this is what we try to find. In case of a classification algorithm particularly, we try to find this function f, so that whatever values of x1 and x2 we give, y comes as pluses and minus as per the data. So in this case, for example, we will try to come up with a mathematical function so that we are able to separate the pluses from the minuses. So looking at this diagram, what is the best way to separate the pluses from the minuses? So intuitively you will see that we can draw a straight line here. We can draw a straight line here, and that line can perfectly separate the pluses from the minuses. So where should we draw a straight line? I can draw a straight line anywhere starting from, let's say, from here, from 2 to 3. I can draw any line parallel to my y-axis and in between 2 and 3. Now this is exactly what a decision tree draws. Decision tree creates decision boundaries. It creates boundaries between classes so that the classes are separated, so that pluses are separated from the minuses or ones are separated from the zeros. So in this case, for example, where should we select the decision boundary? Decision tree typically selects the decision boundary between, at the midpoint of consecutive values of the independent variable. So x1 is my independent variable. The midpoint of consecutive values is 2.5. So here, so it will try to draw a decision boundary here. So this is a decision boundary, and whatever data points you have on the left of the decision boundary are minuses, and whatever you have on the right of the decision boundary is a plus. So how do we denote this? Remember, we are trying to find a mathematical function. Now how do we denote this line as a mathematical function? It is very easy. We can write this line. So this line, the equation of this line is x1 is less than equal to 2.5. So this is the equation of this line. We can write it as an inequality, remember, because we have to focus on the points which are on the left and the points which are on the right. So we have to write it as an inequality. So x1 is less than equal to 2.5. This can have only two results. Either the points can be less than 2.5 or it can be greater than 2.5. So there cannot be three results of this. It can only result in two answers. So one of them will be true. So we typically write the true values on the left hand side and we write the false values on the right hand side. So x1 is less than equal to 2.5. It can be true and it can be false. So what if it is true? If it is true, then what do we get? We get all the minus points. So I will write here minuses. And what if it is true? Sorry, what if it is false? If it is false, we get all the plus points. So this is the mathematical function that we were looking for. This mathematical function, this f is this inequality. And now we have made a very small model which predicts. So how does it predict? It predicts that a point is a minus if the value of x1 is less than or equal to 2.5, and it predicts a plus if the value of x1 is not less than or equal to 2.5. So this is how the model works. This is built on the training data, and once you have the test data, you just put the test data on top of this, and depending on the value of x1 in the test data, it either goes to the left or it goes to the right, and accordingly the output is chosen. So this particular decision that you made here is called as a decision node. This is known as a decision node, also known as root node. Root node because it starts from here. This is the root. So it's like an inverted tree. This is the root of the tree. And the other decisions, the other nodes here, so these two nodes are known as terminal nodes. So these are known as terminal nodes. Terminal because that's where the entire tree ends. These are known as terminal nodes. And this entire structure is known as a tree. Hence, the algorithm is also known as decision tree because it is formed of decisions and it looks like a tree. So these are known as decision tree algorithms or classification tree. These are also known as classification tree. Decision tree is a broad term which includes both classification and regression trees. This particularly what we have built now is a classification tree because it addresses a classification problem. Now you may wonder, we didn't use x2 at all. Yes, we did not use x2 because it was not required. We were able to completely separate the pluses from the minuses just based on one independent variable x1. So x2 was not at all required. So we can say x2 is not significant for this data. x1 alone is enough to separate your pluses from the minuses. Now what are the advantages of a decision tree model over logistic regression model, for example? So the advantages is a logistic regression model is a parametric model, meaning it makes some assumptions on the data. So you can go back to the previous module and see what are the assumptions of logistic regression. It assumes that your data has a linear relationship with log of odds. So it's a parametric model. Parametric means there are some inherent assumptions in the model. But decision tree models are non-parametric model, which means they don't make any assumptions on your data. So there are no assumptions in decision tree model. It doesn't assume any distribution or any kind of property on the inherent data. It is without any assumptions. Hence it is known as a non-parametric model. So this is one advantage of using decision tree over logistic regression. It performs well even if the data is not of a certain kind of a distribution. It can perform well on any kind of a distribution. So now let us move to a slightly complex example. So let's move once again to a slightly complex example. Now here we had data which clearly had a distinction between the pluses and the minuses between the two classes. Not always your data would be so hunky-dory. So what would you do in that case? So let's come to another example here. Same, we have two independent variables x1 and x2, and my dependent variable is y, which takes pluses and minuses. So how do we do now? What do we do? So if we draw a line here, if we draw a decision node here, it wouldn't separate the pluses from the minuses. So what should we do? So in this case, what we will do is one split alone will not be enough to separate my pluses from the minuses. So what we will do is we will go for recursive splits, or we will go for recursive decisions. So we will take a decision, and within those decisions we will take other decisions. So that will help us separate the pluses from the minuses. So in this case, for example, we can make our first split here, or maybe here also. So let us make our first split this time with respect to x2 axis. So let me make a split here. So what is the equation of this decision? The equation of this decision, if you notice, is x2 is less than equal to, let's say this point is 3.5. So I will write x2 is less than equal to 3.5. So this also will have two results. One is true, one is false. So true I will write on the left hand side, false I will write on the right hand side. Now what if it is true? If it is true, it represents this portion. So x2 is less than 3.5 represents this portion. Now this portion has both pluses and minuses. So we cannot write a plus or a minus yet because we haven't come to a conclusion. So what we would do is we will go for an additional split. So we will go for an additional split. Now which variable should we select for a split? Should we select x2 or should we select x1? x2, I don't think if we select any division or partition along x2, it will give us separate minuses and plus. We will have to probably select x1 in this case. So let me select x1 now. I will take a second split here. So I have taken a second split here. Now let me write that in red color. So x2 is less than 3.5 represents this area. Within this area I have split it based on x1 less than 3. So let me write x1 less than equal to 3. This again will have two results, true and false. True on the left hand side will represent this area. Now you see we have a clear distinction between pluses and minuses. So I have only minus here, so I can write only minus here. And on this side I have just pluses, so I will write a plus here. So we are done with this entire area. So x2 is less than 3.5 true. We are done with that. We have correctly classified all the points in this area. Now let's go to the false side. So this side, which represents this area. So we have to now separate these. We can use the same split. We can see the same split works. So I will write x1 less than equal to 3. This also will have two decisions, true and false. True always will be on the left hand side. So on the left hand side, what do you have? We have pluses. So I will write plus here and I will write minus here. So in this case, our mathematical function f is a series of equations, not just one equation. It is a series of decisions. This is my root node, the first node. These are known as terminal nodes. Sorry, these are known as intermediate nodes. These are my terminal nodes. These are my terminal nodes. These are my intermediate nodes since they are in the middle. These are intermediate nodes. And we have a series of equations here. The mathematical function which maps my independent variable with my dependent variable y is a series of functions in this case. And it comprises of both the independent variables x1 and x2. In the previous example, we just used x1. Here we are using both x1 and x2. So x2 is less than 3.5. It represents this area. Now within this area, we are further splitting the data based on x1. Now remember, this split is over and above this split. So this split happens, and on top of that we are having this split. So both apply. So whatever data we have here both these conditions apply, this one and this one, because it is inside that. So it is inside the tree. So this can be like a parent, and this is a child, and this is a child within a child. So the characteristics of the same parents will follow. So these are coming from the same branch. Similarly on this side also. Now we have a perfect classification, and once we have, this is built on the training data. Now how do we predict on new data points on the test data? Now once we have a test data, we will simply drop the test data point on top at the root node, and as per the decisions, it can choose the direction which it will take. So if x2 of the test data is less than or equal to 3.5, it will go on the left hand side. Or if it is false, it will go on the right hand side, and ultimately it will finally drop into any of the terminal nodes, and finally it will take a decision accordingly. So this is how a decision tree typically works in brief. We will go into further details and further maths of decision tree in a later video. But make sure you understand the basics first. You can pause the video, watch it multiple times, and understand the basics before we go into the maths of decision trees.